All right. So in a sense, last time we played around with the fact that there are different forces. We looked at how we can find the bending moment at any spot in a beam, depending on how all the crazy loading is. And we found the shear force that's on it. And now we're actually just going to attach the fact that there's kind of an area connected to that. And this is the idea. Let's see. Make sure I'm in the right world here. You guys have this one, right? Is that your second one? Okay, good. Because you can appreciate, for instance, that actually maybe I could just do this right here. You can appreciate, for instance, that this looks like a cement block, and I'm going to put some weight on it, and you can appreciate that at some point that block would crush, like it would just smash into a billion pieces if you put a bunch of weight on it. But you're not used to weights of that kind, right? Like your car parked on it wouldn't do it. But a skyscraper on top of that would do it. And so it's not just like how much force is there on it, it's also connected to the area that you're trying to put it on. Does that make sense? If I put the same amount of, well, for instance, if I took a pencil and I pushed it against your hand with the point and I didn't push very hard, your skin would resist that. But you could push hard enough, and you've all had lead stuck in your hand, I'm sure, before. You can push hard enough that it does push in. And so what that is a function of area. So I can put weight on that, but if I spread it out, it's kind of the snowshoe concept. It's not just like, how much do I weigh? Oh, you'll sink in the snow. Well, not if you have snowshoes on, you won't. So it's kind of, it's taking force and also getting area involved. Really, that's what stress is about. So since this problem is really small, I think I'll actually just explain it to you right here. So there's really two kinds of stress. One of them is called normal stress. And we've been dealing with the concept of normal for quite some time, and normal really gets at the idea that it's perpendicular to something. And then there's also shear stress. So the idea is kind of like this. Like the first time I ever started building some houses, there were rafters in it that were so long that there wasn't lumber long enough to make them. So I remember the framer, I was kind of surprised by this because I've tried to avoid this forever in my own construction work that I've done. But he basically did this. He took two pieces of wood and spliced them together like that. He put kind of a long cut in them instead of just like putting them butt to butt like this. Kind of to like that. He put this super long, and it was way longer than even what I drew. It was more like this, super sharp and skinny. And I actually kind of understand that now for the first time. Does it make sense? You have way more surface area to work with right there if you make that cut super long. So if you're going to glue it or screw it or whatever it is you do, and in his case, he just came back and put like another piece of plywood over the top of that and just nailed the crap out of both sides of it. And maybe put glue inside there too, but it's like that actually makes sense. And so in the end, so he makes one board out of two different boards. Well, of course, in concept, that's something we're going to do all the time in engineering, right? You're going to join stuff to stuff. You can see you have metal desk legs. I'm sure you haven't looked underneath there, but there's probably some kind of bolts or screws that screw the legs into this particle board. And so you're making a connection there between steel and wood. And obviously I'd like that to be able to withstand, whatever a person might end up doing to it. But basically, this is the concept. Normal stress. It's basically in this direction. It's abbreviated with an N, abbreviated with a V. And we played with that stuff yesterday, right? Remember how we usually had nothing for the normal stress? but we did have a shear stress. The key is the shear stress is really going in this direction. It's ultimately in the plane. I guess I'll say intersection, in the plane of intersection. I'll just say in the plane of intersect. It's in that plane or parallel to that plane. So if you did try to pull that apart, there is a desire for that to kind of shear. Notice in this case, it isn't perpendicular because of the way the person put the joint together. The slices we made through things in the last few days, we always cut it kind of perpendicular, and that was our slice. But in this particular case, that's like joining a couple of pieces together. So shearing is basically shearing along that line, whereas normal is actually, well, normal, perpendicular to something. So that cut can actually be at an angle. So you could weld a couple of pieces of metal together, and then maybe that weld would be a weak spot. And so this is perpendicular to the plane of intersection. And secondly, how are these stresses measured? Well, ultimately they're measured in pounds per square inch. And that's exactly the point I was talking about earlier. Like if I put a force of 2 pounds on a pencil into your finger, that's 2 pounds. But if the pencil is sharp, that might push it into your finger. But if the pencil's not sharp, it won't, right? So you don't just say pounds, you also get area involved. So PSI, which is probably something you've heard before, and that is a super common way of measuring force of something, including area. It's kind of force relative to area. So PSI is short for pounds per square inch. PSI is actually a fractional statement. So my compressor, for instance, is measuring that. I mean, I heat that thing up and it's got 100 pounds of pressure on. For the most part, from my perspective, I'm just shooting nails into wood. And so all I know is when it was set 100 on there, when that dial said 100, I don't even know what it meant. When it said 100 and I shot the nail went too far into the wood. So then I backed it off to 80, shot it again, and it was like, oh, okay, that's good. You see what I'm saying? It's like the average person doesn't have to have a working knowledge of this. It's just a measurement. And I just know 80 worked and 100 did not work. So now we're going to get force, but we're also going to, and this is where kind of the concept of stress gets involved. So it's kind of like how much stress is that block that we're about to tackle in a minute? How much stress is it under? Well, it depends on the pounds. It depends on the area. How much weight, how much area? If I have a lot of weight, fine. If you have a lot of area, no problem. If you have a little weight, then you can have a little area. So huge, like this is something you want to get really well, and you probably get it really well whether you want to or not. That's the same for shear stress. It's just a question of what direction is it in. Let's see, what would metric be then? Notice the units there are inches, and that's mainly because when you connect two things, usually you're talking about something small that would be measured in inches. Does that make sense? If it was a skyscraper or something, maybe I'd have something that was in feet, but the average support or something of that nature is, I mean, the footings that I draw, for instance, for full houses are like 16 inches. So it doesn't make sense to call those feet, because then it'd be something like 1.7 feet or something kind of weird. So what do you think metric would be then? What would be the units for if this was metric? What's metric version of pounds? Newtons. Kilograms will produce the pounds, but when it was in metric, our force was in newtons, whereas in our system, it's in pounds. And then the measurement could be, well, it's still an area, but it could be like square centimeters, square millimeters, but it turns out oddly contradictory to what I just said to be meters. Now, of course, PSI is kind of like a new name for pounds per square inch, but notice PSI, pounds square inches, like that actually makes sense, right? But what are you going to do with newtons per square meter force divided by area? Well, somebody thought, oh, let's just make up a new name. And of course, this is nice and simultaneously annoying, right? It's nice that we get really weird units that have a big combination of things. And this is something we saw quite a bit even in dynamics last term or statics last term. Anytime something gets really complicated, we invent a new name for it. And so we're going to have a lot of that in both this class and also in dynamics if you're in there. So that's nice because it simplifies it. Now I just have this unit called pascals. I assume, although extra credit if you want to go research this, I assume that's Blaise Pascal. Have you heard of that dude? He's one of the famous mathematicians. He's kind of one of the top 12 names that would come up if you research famous mathematicians. Guy was a stud, created a lot of really cool things. Also a philosopher. He was sort of criticized because he invented quite a bit of really cool mathematics, but then he got off into religion. And then, then he didn't produce anything cool with math anymore, and the mathematical people were mad. But interestingly, most famous mathematicians, are thinkers about the universe and that business of, dimensions that we were talking about in 261 and so forth. It's like inevitably people should spend some time questioning, is there a God in the world? And deep thinkers can go a lot further down that road than other folks. And so that's the little that I know about him. But I have a feeling this was either named by him or in his honor. So you'll notice in the back of the book, for instance, that the answer will be in pascals if you're lucky, but more likely it'll be kilopascals or megapascals. Remember, kilo is 1,000 pascals. Mega would be 1,000,000 pascals. And so you get some really large forces when you're talking about larger objects. And so that's going to come up. I find myself, just as a side note, maybe it's because I'm new at this, but I find myself always wanting to change the units for all of these into pounds and inches and just work in that so that when I'm done, I get PSI, even if the answer is like 897 million PSI or something, and that at least I kind of know the right answer, it's in the right units. Or if I'm doing a problem and it's metric and they give me the measurements in millimeters or something, I find myself wanting to change them to meters just so that it'll end up, in pascals, end up kind of in the right language. That will be maybe a little bit of a problem for you in this section.
As an American, can we just expect inches?
That's a super good question, and the answer is not really. It sort of depends on the magnitude of the projects you work on. Around here, you would not see pascals for anything if it was kind of a house project, but a lot of times when you jump to the bigger stuff, like when they built that interchange at the South Medford a few years ago, the I-beams into that were 7 feet tall, and they're just really cool. And so I went over to the construction office and was bugging them about it, just trying to figure some things out about it for math, and because I think it's cool. And I noticed all the measurements on it were in metric. I was super surprised by that because people just don't think metric around here. But when it's a large scale project and it sort of has a worldwide, like that design might be stolen from some bridge they built in some other place. Everybody but us uses this. And then of course all the math, if you get used to working in centimeters, you don't have all these nonsense fractions to work with. Your tape measure is just so much easier to read and so forth. So yeah, all the engineering stuff that I get involved in with my house plans, all PSI, all. But I see kips constantly because there's never weights that are like 400 pounds. That's tiny. That's 2 people. When you're talking about holding a house up, you're talking about thousands and thousands of pounds. And so kips are everywhere, thousands of pounds. You'll see KSI. Maybe I should say that here. KSI, which would be 1,000 PSI. So it's like kilosquare inches. It doesn't work so good. You see what I'm saying? It's like kilopounds per square inch. It's not KPSI. It seems like it should be KPSI, but you'll see KSI. And so you got to kind of recognize that. Little side note, I'm kind of, working on some notes for this. Oh, that's not cool. It came up weird. So I'm kind of working on a note page just because some of this stuff gets a little cumbersome. Wow, I should have saved this as a PDF file. It got all screwed up. But I'll show you this later and print a copy of it for you and so forth. But notice we're talking about normal stress and shear stress. Notice they have a couple of abbreviations for them, sigma, which you do recognize most likely. And then that bottom one, anybody know what that is? Mathematicians are sort of famous for bringing up Greek letters. It's tau. How the heck do you know that?
I was gonna say physics.
Is it
I remember
physics? Showed up in physics? Interesting. So notice here I said normal stress is perpendicular to the surface and shear stress is parallel to the surface. Like I'm just putting that in the notes and I'm giving you the formula for how to calculate it, so forth. So, that note sheet will be kind of a working document. We'll work on it together. But let's add that to this now and say here, normal stress is abbreviated with the Greek letter sigma. Shear stress is abbreviated with the Greek letter, I think it's spelled tau, T-A-U, I think is how it's spelled. So again, from my perspective, or from your perspective as a student, that saves time if that symbol is written in the book, but it turns almost into a foreign language that you got to read. Like for a while, it's like, wait, what are these letters? And so I feel like for a test, you should have a list of all that junk, like right in front of you, so you don't have to think about it. And then again, the argument of like, in a sense, do the assignment for today's discussion tonight so that you can get this stuff right, get it in your head, help this kind of language get into your head. So notice the units tell you this, but notice it's pounds divided by square inches. So naturally this would be something like that. N for normal, the normal force. In this case, it's kind of weird because it's like normal for newtons. But I'm really taking a force and dividing by an area every single time. And I do the same thing with tau. It's just that to get tau, I'm dividing the shear divided by the area. And really those are just directional. It's like how much force is there to rip something apart and how much force is there to make it kind of slide along its axis, if that makes sense. So have a good sense of what it means for something to kind of rip in half straight apart in the normal direction. That's normal stress, and shear stress is kind of a fault line, which is what happens when we have earthquakes. They slide along each other. So that's the difference. They're both forces getting to formerly connected objects not to be connected anymore. It's just kind of a question of what direction do they go in. Okay, so let's take a look at this. So these are kind of the main formulas. And what I like about this is PSI. In a sense, all I really need to remember personally is kind of PSI, because that just tells you, oh, it's pounds divided by area. Like I don't need those formulas down below. It's pounds and square inches. Go find the pounds, go find the square inches, divide them, and you got PSI. This is not hard if you take that approach. So let's take a look at this brick. This is a pretty easy question. Notice the unit, 6 kips. In other words, 6,000 pounds. Again, I find my gut reaction to be to change that to 6,000, because then it's pounds and then I'll get pounds per square inch. Could I just leave it as kips and then write it as kilopounds per square inch? Maybe. I don't know. So 6 kips equals 6,000 pounds. Kilopounds. So I've got that much force pushing down on this brick. So that's awesome. But then I've got an area there. Notice that's not a complicated area. It's just a bunch of rectangles and so forth. So I can find the area that's on that brick. Incidentally, as a side note, does it make sense if that 6,000 pounds was placed on it? Well, kind of the way I said earlier, like a pen on a pencil on your finger or whatever, does it make sense the brick could kind of crush in? This problem is actually assuming that it isn't actually going to puncture that shape, which is actually not automatic. So for instance, when I draw house plans and I spec a big footing like this, because I know Earth holds 1,500 pounds per square foot, not square inch, but 1,500 pounds per square foot. I can't draw a gigantic footing that's 60 inches wide, which I often have to draw something like that, because if you put a post on it, it's just going to puncture it. You see what I'm saying? It's not going to stay flat and just go into the ground like this, it's gonna go break in the middle. So what I have to do is put a bunch of rebar in it both directions. Rebars, have you seen rebar? It's like 1/2 inch in diameter stuff, and I'll make a grid out of it going this way and a grid out of it going that way. And that way, when you do put a post in the middle, it will make it all act as one and sink uniformly into the ground. And so notice in this case, did they say anything about that to us here, or did they just go, they'll never think of that? Yeah, they didn't say anything about it. I'll leave this hanging for now, but it says show the stress acting on a differential volume element. I mean, I find myself going, huh? I'll let that hang for just a minute. So the point is like the key word that needs to stand out for this is just the word stress, normal stress. So when I see the word stress, then I'm PSI, pounds per square inch. Next chapter in chapter 2, which we won't do till a week from today, but then we're going to be talking about strain, and stress and strain are the two kind of the big things. And so for right now, when I see the word stress, I think, oh yeah, pounds per square inch. Good. Give me some pounds, give me some square inches. I'm done. This is easy. But for a long time when I was first learning this, I kept mixing those two things up because they're just brand new words I don't never seen before, and I flip flop them all the time. Well, there's more than one way to find the area of the top of this. I won't bore you with the details, but just as a side note, probably the smartest way here is to surround the entire shape with a rectangle. So that would be 12 plus 1 plus 1. That would be 14 by 4 plus 1 plus 1, 6. So find the area of the whole top, 14 by 6, and then go back and subtract these little shapes out would probably be easier. So if I took, for the area, if I took 14 times 6 and then subtracted off 2 of those 4 by 1s, that's probably the easiest. So that brick is 76 square inches. And so ignoring whatever the heck differential volume element means, then my normal stress, and notice that symbol takes care of the normal stress. We've decided that that's the definition. I mean, that's the symbol for normal stress, perpendicular. Do you notice that arrow is going down perpendicularly into the block? It isn't kind of aiming at a different angle. So the weight is loaded on top of it that way, and that'll be the most common one for you as an engineer. So then, okay, that's easy. Got the right units here, 6,000 pounds divided by 76 square inches. I divide that out and I get 78.9 pounds per square inch, or better written PSI. That's not hard. That's the concept. Now, the interesting thing is you could actually go look up concrete and see how strong is a concrete block. Will it withstand that? So one of the things that's interesting is if you order concrete, like at the concrete company, for a driveway or whatever, you don't think too much about it when you're kind of doing construction because they kind of deliver the same stuff out all the time. But that concrete is called 2000 PSI concrete. In other words, it's guaranteeing it will hold 2,000 pounds per square inch. So notice, yeah, the concrete's going to hold 78 pounds per square inch, no problem. It's not, the concrete's not going to break. But that's not a given. Does that make sense? Aren't there materials that would not be able to handle? And notice that's per square inch. Like, don't forget to stop to think about that. That's 78 pounds, roughly 80 pounds on every tiny 1 by 1 inch, right? So it's spreading out that 6,000 pounds. And as I said before, if you were going to puncture that, you might have to put a steel plate on the top of it to make sure that they got distributed out everywhere. Because if you put a post in the middle of that, probably those little tiny protrusions aren't going to be helping. You see what I mean? They're like too far out there. So this is assuming it's actually spread evenly and so forth. Now, what's this differential volume element? What the heck is that statement? What's that?
Different thicknesses of material.
Not that hard, actually. So differential is like derivative, which just means stuff is tiny. So they're basically just saying, show the stress acting on a tiny chunk of it. Well, that's exactly what we just did. We said there's 78 pounds on 1 square inch. So differential means tiny. Because then when we find the slope of something, we found the slope of just a tiny section of the curve, right? So when I first read that, I was like, what in the heck are you talking about? But then I realized, oh, okay, they're just, but I don't think that's very good as an author to include stuff like that. Because students aren't going to understand what you mean, but this isn't hard. That's the two things that you got to know, and then divide them. And so this is one of the huge, as I mentioned, one of the huge things, because almost all materials have a PSI. That's one of the things you could look up about it. And then you would know whether you're asking too much of that to do its job. Okay, cool. Let's do something slightly more challenging. And this is the same question, actually, but I just have to work a little harder to get the 6,000. Last time they told us, oh, it's 6,000 pounds. Awesome. Well, here I'm told, and notice this is a Newton problem. They said P is 40 kilonewtons. And so incidentally, did you notice last time my method worked really good? Because when I divided 6,000 by 76 or whatever that number was, it came out a reasonable PSI number. Like it was kind of good that I did that. I got lucky. Well, notice my inclination for this one is to go, oh, look, kilonewtons. Well, I know the units for this are newtons per square meter. That's the generic way of saying it. So I find myself wanting to call that 40,000 newtons. Maybe this time it will be a bad idea that I do that. So I'm actually not saying you should kind of do what I'm doing, but I just find myself wanting to keep this simple and understand that, oh, okay, this time it's newtons divided by square meters. And so I want newtons and meters. And that's what I'm going to make for what I'm doing. And then notice the units on that are meters, like those links are meters. And so that kind of makes me feel good. So maybe my idea won't work so good this time. But notice this force is actually not pushing directly on anything. And so what they're asking me here is to determine the average, again, normal stress, perpendicular stress in each of the 20 millimeter diameter bars. Darn, millimeters, right? That's not meters. Let's see, bars, 20 millimeter diameter. Diameter, what's that code for? This is really important. I'm always screwing this up. What shape are those bars? They're circular because of the word diameter. So you got to look for that. Sometimes you'll think they're diameters. Sometimes the measurement you'll given will be diameter. Sometimes it won't. They could have said 20 millimeter square bars. It'd be nice if they said the word square. If they just said 20 millimeter bars without the word diameter, I'd be confused. I don't know. What do you mean by that? Is it 20 by 20 or is it 20 diameter? So I certainly wouldn't want my test to be confusing in that regard. But this time the area, so what I really have then is, in a sense, I have this bar. I'm going to erase this, but I have a cross section of this bar with the diameter of 20 millimeters. And I'm interested in the force that either goes this way or this way. In a sense, I don't really care. By the way, if it was pulling in this direction, does that make sense? That's a tension force. So it's a certain amount of tension force that's being applied to that bar, which might tear it apart. And again, that's the thing. If it was a certain kind of steel, I'd want to be able to look up how much PSI can this steel withstand. If the arrow is going this way, it's compression. It's still the same calculation. It's still the same PSI number, but maybe that's interesting to note. So this would be tension. This would be compression. I know there are some problems where they actually ask you to say that, like say which one it is. But notice they said in each of the 20 millimeter diameter bars, and notice there's 3 of them. So they're all the same size, but that P up there is not going to give me the same force. And so this is hearkening back to the section we just did and also back to statics. Can you translate that 40,000 newtons, which is in none of the bars? Do you understand that? That's in no bars. But can you translate that by drawing free body diagrams of each of the joints? This is what we did in statics with respect to a truss. How much force is going to be axially along each of those bars? Because I got to convert that force to be, well, as we drew over here, kind of perpendicular to my cut, perpendicular to my slice over there. So, how should I proceed? Well, I find myself wanting to kind of go to this spot up here and say, well, if it's pushing to the right, this bar can't do anything about that, right? This is just kind of a review of truss design. That bar can't do anything about it, but this bar can, and it would have to push back in that direction, which means it's also pushing in that direction. That's the only bar that can stop C from moving to the right. So I need this to stay static, and so I can calculate that. So I could say, I'll call that force BC. So I could say sum of the forces in X, and maybe I should say this is all particularly at the point C, it's not just everywhere. So I got 40,000 newtons to the right, and I've got force of BC to the left. That's why I made it negative, but remember that's not horizontal. Notice this shape right here, since they were actually really nice to us, but you probably don't notice it here. If I doubled this number, it's 3, and if I double that number, it's 4. Oh, this is a 3, 4, 5 triangle. It wasn't quite as obvious, but really this is a 3, 4, 5 over here. So that those two dimensions are actually only there to tell me what angle that bar is at, because they didn't give me any degrees. So what fraction of that force BC is horizontal then? 4/5 of it. And that's it. That's the only thing that's going to stabilize that going in that direction. And so now I can calculate force BC, which is actually 50 kilonewtons or 50,000 newtons. So that bar then is basically being smashed. It's being compressed. We call that compression. That's a lot of force. But remember, and this is what I hope really sinks into your head, we stopped before and said, okay, we're done, 50,000. But does it make sense how important the diameter that is? Like you can't just ignore that. Something skinny is not going to be able to handle that much force, or maybe it won't, maybe it'll be able to handle, but it'll kind of bow outwards. Does that make sense? You put a bunch of force on it and it doesn't break, but it bows outwards. Well, now I know the force. All I need to know is the area. Let's go ahead and let's see. Yeah, let's go ahead and finish it. They told us. Now let's see, let's do something here. So we're talking about the area of a circle. Area of a circle is equal to pi times the radius squared. As a time saver, do you agree that radius is diameter cut in half? Now what you could do is say, oh, 20 millimeter diameter, that's 10 millimeter radius, and I'll throw 10 in there. Absolutely nothing wrong with that. But a time saver is sometime, I don't know if this is actually a time saver, but if I replace radius with d divided by 2 and actually square that, does it make sense? That turns into p times d squared over 4. Sometime in this book, you're going to see that a lot, because that's kind of, I mean, if the diameter had been something like 17, does it make sense? It would have been nice not to have to cut it in half. So you could actually just take the diameter and square it, multiply by pi, but then divide your answer by 4 and then not have to cut that in half. Just a side note. So if that's the case, the area is equal to pi times diameter. But again, I find myself wanting to be in meters, so I can write this in pascals. So 20 milla's 1,000th. So I got to move the decimal point 3 places to the left. So that'd be 0.02 meters. Does that make sense? And so that written down. So again, there's nothing wrong with doing this in millimeters. It's just that when you get all done, your answer might not match what's in the back of the book. 0.02 squared times pi divided by 4. I got kind of a ridiculously small number, 0.0003116. That'd be square meters, wouldn't it? So of course that kind of makes sense. If it's a bar that's measured in millimeters and you try to make it square meters, it's going to be a ridiculously tiny number. Well, notice I have the ingredients now. I have a weight, I have a force, and I have an area. Divide them. But can you tell what's going to happen when you divide this? So let's see. Notice the way I label this, because it's like I got 3 answers here. So why don't I call this the stress of BC, all right? not just stress, but stress of BC. Well, then I'm going to divide those two numbers. And maybe you recognize that 50,000 is already large. And then when I divide by that other number, which is really tiny, I'm going to get an astronomical number. So this time I think my idea kind of shot me in the foot. I should have left that as kilonewtons. That'd be 50 kN. I'd be dividing 50 by that number. It wouldn't be so weird. But again, there's nothing wrong with this. I'm going to go ahead and put these units back in it because I just want you to notice this. And these two numbers are still in my calculator, by the way. So even though I wrote down 0.00316, that number is still in my calculator. So I'm going to say 50,000 divided by answer. And I get, oh my gosh, what do I get? I can't even write this down. 159, 154, 943 pascals, newtons per square meter. Great. You're taking a test, you're done. Great. What do you think you're going to see in the back of the book, though? Not even kilo. Because remember, you can only have 3 numbers because that many numbers is annoying. So you move 3 at a time. That's still a 6-digit number. You move another 3. So what have you done?
Megascale.
You went kilo and then you went mega. So this would be in the back of the book as 159 capital M megapascals. Like that's what you'd see in the back of the book. They're both right. I could care less. But you can appreciate just to copy, like for me to stare at my calculator and even copy that number down correctly is dangerous business. And if I miss one number, that's a factor of 10, which means people die. It's not just, oops, I missed one number. So you can see why engineers say, hey, let's just have 3 numbers. Then you're not going to make those kind of mistakes. That's a great idea. Interestingly, as a side note, I'm watching airplane training videos, and I got to the communication section last night because I don't know if you've ever heard anybody talk who's talking to the tower, but it's like, what in the world language are they speaking? And again, it's the same thing because there's all these people on the same channel talking, and you can't just be, hey, how's your day? You know, it's got to be very precise. And for instance, 9, you don't say 9 because it doesn't sound very clear. So you say niner, and then all the letters of the alphabet. You don't say the letters, you say the Alpha Bravo Charlie version of those whenever you're saying letters. And that's just to make sure that, because I'm about to crash into someone if I get this wrong, right? So it's the same kind of in your language or in your world. So anyway, that's just interesting. So do you see how easy this is if you just say, hey, you know, newtons per square meter, go find newtons, go find square meters. In this case, though, we had to work a little harder. We had to use some things we already know from the past to kind of get us to that point. Well, maybe we won't do all of these, but let's proceed to somewhere else. Well, what about, well, this is what I find so interesting about this. If I go back and kind of erase this for a second, does it make sense there's no force on AC? There's no force on that at all because that force is sideways, right? And yet, to balance it vertically, we had to have a force there, which now all of a sudden means there is a force upwards. You see what I'm saying? Isn't it interesting? My first thought could be no force on AC, so there's no PSI. That could just be a piece of string. No, that other force over there resulted in an upward force. And so now all of a sudden there is a sum of the forces in Y. So if I say the sum of the forces in Y, that would be, and again, notice by logic, you already know whether that bar AC is in tension or compression. Since BC is pushing it up, then this is going to have to pull down, which means, or pull together, maybe is another way of saying it. So this one is actually in tension, and this one over here was in compression based on that. That's not something you want to, oh yeah, I did that last term and I forgot it. Like this is something you got to know permanently as an engineer. So this one's already in tension. I know that. And so now I got to balance C in the Y direction. So I've got force of BC pushing up, but it's modification for pushing up since it's not actually just pushing up, it's 3/5, right? And that's pushing up. And then I just figured out that the force of AC is actually pushing down. So I'll make it negative, and that's got to be 0. And of course, I figured out a second ago that force of BC was actually 50,000 newtons. Conveniently, 50,000 newtons divided by 5 is 10,000 times 3 is 3,000. So I could kind of do this in my head. Force of AC then would be 3,000. Sorry, 30,000. So again, it's kind of cool to say, oh, look, that bar has 30,000 newtons of force. But again, the cool thing here is we're not quitting there. We're saying, okay, cool. Well, then let's go find the stress that's actually on that bar. Stress on bar AC. Well, of course, I take the newtons divided by the area, which hasn't changed because they didn't change what bar was in this. And I'll just write this one down to save us a little bit of time. You end up with, for AC, 95.5 megapascals. Notice it's significantly less, which actually means we could use a smaller bar here. If it was the same exact material, then this one's overbuilt. We could use a smaller diameter bar potentially for this one. So I'm very interested to understand why it's so important that we just took one more step from last term, because now you can actually choose a material.
I have a question.
Go ahead.
Mistakenly, I kind of just did like the stress. So I did like F of Y, but with stresses instead. And I got the same answer.
Oh, interesting question. In other words, you ever understand what he said? He said he took this number and used that number and kind of, in a sense, made this calculation and got 95.5 anyway.
Yeah, so 159 times 3/5 is, I got 95.4. So it's like a
Yeah.
rounding thing.
Yeah, that's totally true. That is 100%
So
true.
that's not a fluke. That's like,
No.
we kind of operate like that. If that's
It
what
could
we're
be done,
looking for.
yeah. Now that worked because all these bars are the same size. If that
Right.
other bar had been a different size, then we wouldn't be able to do that, but yeah.
Yeah.
It's interesting because like the lengths are proportionate to each other, 3, 4, 5. The forces are proportionate to each other, and now all these stresses are proportionate to each other too. So that's an outstanding observation that I did not make when I was learning, when I was doing this.
I wouldn't say observation. Stumbling upon.
Yeah, you stumbled upon brilliance. I'll just write the last one down without doing it because we're not going to learn anything new by proceeding, but just if you're curious, the last one, if you kind of want to check it for yourself, AB, turns out to be in the middle, 127 megapascals. But of course, I'd have to proceed to a new joint now for that one. Does it make sense? Incidentally, notice these two connections down here. What do you notice about how many forces does that connection resist? If I was going to add those to the free body diagram. Notice it's pin connected and bolted to the ground. So it would not resist rotation. It appears, and this isn't part of the problem, but it appears that it has like a bolt going through, which means it would rotate. So it's not resisting moment, but it would resist X and Y. So I'd have a force in X and force in Y. What do you notice about this one though? Have you seen that enough that you kind of recognize what he's trying to draw there? That's a roller, yeah. So it actually only resists in the Y. And that's because of thermal expansion, which we'll be talking about later on in this class. If something gets warm, it's going to expand. And if it can move, that'd be great. Because if I expand something, and I'll have a really neat problem about this. Was this today or later? Later. It's going to want to get longer. It'd be nice if it didn't cause stress in it. Just if it was pinned on both sides, and this is something we'll be talking about when we get to strain, but if it's pinned on both sides and it gets warmer, it's going to get longer, which is actually putting internal force on it that you just can't see. So that allows it to move. So anyway, that's just interesting. So anyway, I'd have to proceed over here, right? In order to get this one, I see, oh, look, as a result of that pushing to the downward and to an angle, this is going to have to pull back in this direction. So I can see that this last one is also going to be under tension. So as soon as I found that tension number, then I could divide by the same area and I'd get my answer for that one too. So then that whole thing would be in balance without the need for those, without the need for, too much work to be done. But does it make sense? This would be required of that joint over there because the red's also pushing down and the blue's not going to help that. So that blue would have to be there. That force at B would actually have to, there is going to be a force there. So the question is, is that going to smash into the concrete? Is that little connection going to break? Is the pin that it's on going to shear off? I mean, these are all things we still have to think about. That's what we're studying right now. Some of your questions in your assignment will ask about that pin. Will it shear off with this much weight being on it? And over here, notice it's got green going up, which means this is actually going to have to hold that to the ground. Isn't that interesting? And then you've got that A, B pulling to the right, which means this is going to have to pull back to the left. So that really is required to have two different forces on it. So you see why he put the connections on there he did, even though we aren't really having to pay any attention to that. Also, with these bolts down here, so if you picture a bolt kind of going down into whatever that goes into, does it make sense if that was being pulled on in some way that those bolts could also just slice right off like scissors? Again, that's shear, perpendicular, or parallel to the cut, so to speak. All right, how's your brain?
So if you gave us the AB, but are you saying what you would have had to do is kind of do the moment around A and get that Y?
Well, we just have to do this one more, like this calculation we just did over here to convert 50,000 to 30,000. We'd just be doing the same thing over here. Like we know that this force right here is 50,000. So if we said, okay, well, 4/5 of 50,000 are trying to get it to go this way. 4/5 of 50,000 is 40,000. So this would be 40,000. So then this would be 40,000 divided by our area, and that's where 127 came from.
Can you give me Agnes, normal stress of that baby? Or 127? And it asks for like the average, so we just average all these, right?
Yeah, now why does it keep saying average? Why does it say average normal stress? Well, that's just because, as I said before, if you put a post on top of, if I put weight on top of this right here and I put it like this, and so I got 200 pounds of dirt pushing down on this right now. Is it averaged over the whole thing? Like, is this table able to take this and like, work it all the way out to the side so this is doing the job too? Or is this actually going to puncture right through here? So when they say average, they're saying, although I'm putting 200 pounds here, it could actually only transfer out to being 100 pounds out there. You see what I'm saying? If you kind of average it out, it would be the same PSI force all the way down. Well, if I put a huge thick steel plate on top of this, that would cause the 200 to spread evenly across it. So they're saying average normal stress because you actually can't calculate every single differential element, every single square inch of this may not be the same. So that's kind of interesting. It's an awesome question. Again, always interrupt because I'll get to rambling. What about this guy? So here's where we finally get a question that involves a shear. We've done two normal stresses, but now, and you're definitely going to see a question like this on the test. This is what I showed you at the start of class, where you have this block that's joined together. Notice the block is under compression right now. It has the arrows. Notice the forces that are acting on it are squeezing it from the top and the bottom. And so notice they're balanced, in which case the block isn't wanting to move up and down because it's being pushed on equally. So the better way to think of this is it's kind of like the block is sitting on the ground. And because it has 600 newtons pushing on the top of it, then Newton's laws, for every action, there's an equal and opposite reaction. That means the ground is going to have to push up at 600 as well. And so the block is feeling compression. So it's having to push back, arrows out to kind of keep from squishing. But notice, in a sense, there's this section AA, like somebody made a cut through it. Or you could think of it as a piece of steel and they kind of welded it together. This drawing isn't very good, so I'm going to add to it a little bit. don't know if this helps or makes it worse, but does it make sense if you actually sliced through it? Now that I colored in, it probably makes it worse, but if you slice through it, that's kind of a rectangle that you sliced right there. And they made it look like it was a line, but it's really not a line. Maybe I'll exaggerate it and do it a little bit better. Trying to stay parallel to that line, but it didn't work very good. So I'm going to make it exaggerate away from it a little bit. Does it make sense? That's really what your slice would look like if you slice through this with a saw. It's not a line, it's a plane. And so it's at 30 degrees. And so that's causing, well, stress inside. And it's a pretty good name for that. It's causing stress inside this block. And the question will be, it looks like it's made out of wood. The question will be, will the fibers of wood kind of be able to handle that? Well, again, there's PSI numbers for how strong all kinds of different wood are. So as soon as we figure this out, we're going to be able to say, will your piece of hemlock be able to handle 600 newtons of force? And if the answer is no, then we better do something different. Notice we're not talking about the wood itself. We're actually talking about the joint, almost like they glued it together. So will the joint rip is kind of what we're talking about here. If this is just a piece of wood, it's not going to just on its own want to rip in a diagonal. Does that make sense? It would have to be, I welded it like that, and will that hold is really the more logical way to look at it. So does it make sense? I got to think a little bit to get the area of that thing, because now it's not just, you know, a rectangle anymore. I mean, it's not just the same as the top of this anymore, because the cut wasn't made perpendicular to that. The joint wasn't made, you know, square to that. So I got to do some calculations, don't I, to get that area. So given that they're asking me for, notice they say it's made out of plastic. What's this statement about? Assuming that the caps at the top and the bottom distribute the load uniformly throughout the block. What is that? It's exactly what I was just saying. If you point load that, is it actually going to spread across the top of it? So they're trying to maybe alleviate a question somebody might have about that. In other words, is that a point pointing on it? Is that a pencil sitting on it? If it is, it's not going to distribute all the way out. So that's why we're finding average. And notice they ask us for the average normal and average shear stress along that section. And by the way, that's how you label sections. You're going to need to start thinking about how you label stuff. But when I draw house plans, I draw a section through the house all the time and show staircases and stuff. And so it's really nice if on the floor plan, I draw some kind of a line that says this is section, you know, AA, and then they can look over and see the side view of it. So let's do normal first, just because we did that already. But what's tricky about this? Well, remember what direction is normal in this picture? Because this is different now. Perpendicular to the plane of the cut. So in other words, that's the normal, perpendicular to that plane. Before, that was just kind of automatic, if you will, but here it's such a weird angle, that's not near as obvious. So I got to find the force in that direction. Does that make sense? The force is not 600 now, because it has to be perpendicular. And again, the idea here is kind of XY axis related. Like we had a lot of success in 211 cutting everything into XY axes, and that's kind of what's happening here. And so then the shear, and again, I don't know which way to draw that arrow. Do I draw it up or I draw it down? I don't really care. And shear is going along this plane, like more kind of in that direction. So I just need to know what those two forces are, and then I just divide them by the area of that red rectangle. That's really the key to this. Okay, well, what size is that rectangle? Well, notice I know this over here is 50. I know the rectangle is 50, but then it's 50 by a longer number. It would have been 50 plus 50 down here, which is 100, but it's longer than that, right? So in a sense, that distance is 100, but I need to know that length, don't I? Well, now that I can see I made a right triangle out of this, I could say, oh, 100 is adjacent and L is the hypotenuse. That's a cosine problem. So I could say the cosine of 30 is adjacent over hypotenuse. And say again?
So it'll be 100 divided by cosine of 30.
Yep, that's exactly right. 100 divided by the cosine of 30. I can't remember if I already had that written down. It's 115.47. And since this is millimeters, I guess I'm still in millimeters right now. Maybe I'll change that later. Incidentally, another side note, but I don't know how good you are at drawing, but let me just do this really quick. Just for practice. Here's an isometric view. Well, remember that this is kind of what we've been doing in the past. If you take off in these directions, these are kind of the 4 directions for X, Y, and Z. So what I'm going to try to do is stay parallel to those. This sketching skill that I'm just giving you a chance to think about here. One of the things that would be nice for this drawing is to kind of redraw it as a section. So notice I'm trying to stay, do you see those 2 lines are parallel to the XY lines over there? So this is the front end of this, trying to stay parallel right there. But then I've got this cut in it, so that this side is actually taller than the other side. So wouldn't that be kind of nice to be able to draw something like that so that you could actually show the shear force going off in this direction and the normal force going off in that direction. And we just figured out that this was 115.47. I'll just remember it's millimeters, and this was 50 millimeters up here. It's kind of cool to make an isometric drawing. It's kind of neat to be able to do that. So this is our plane that we're chopping. That's the plane we're interested in. So now I can say my area then is whatever 50 times that number is. That number's still in my calculator. So if I say times 50, I get some huge number. But again, this time I didn't change it. So I'm kind of trying to decide, should I change it? What if I decided to change it afterwards? Since those are millimeters, does it make sense if I divided this by 1,000? That would change one of those 2 millimeters. And then if I did it again, that would change the other one. So I could call it 0.0577 square meters now if I wanted to. So I could say it's 5,773.5 square millimeters, or 0.05773 square meters. Again, I find myself inclined toward just wanting to leave the units so that it's in pascals, because that's kind of what I'm going to see in the back, and that's the standard. PSI is the only way you're ever going to see anything that's pressure, so you're sort of forced to change it to pounds and square inches. One thing to be careful about, just as a side note, but the untrained person, that if they get to this point and get square millimeters, they'll like, oh, 1,000, so I'll divide by 1,000, so it's 5.73, and you know that you'll get it wrong if you do that. Actually, I got it wrong. There's more zeros there. I was thinking, how come there's actually one more zero on that? I divided by 100, even though I said 1,000. So the untrained person would say, oh, I just have to divide by 1,000, so that'd be 5.77 square meters. Well, that'd be a mistake that's going to cost some lives. So I've got my area. I just need to convert those 2 forces. How am I going to get 600 converted to those 2 directions? Again, this is geometrically kind of challenging. Anybody have any good ideas? How do I get 600 to be going the right direction? Let me see. I'll draw a little bit for you while you're thinking about that. It's kind of like 600 is going here.
I had a question. There's a 600 Newton force underneath there. How's that applied?
Say that again.
There's a 600 Newton force applied underneath it.
That's important that it's there, because that basically means the block is static. Because remember, if I took this dish right here and I pushed up on it, it just goes up forever, which means it doesn't experience any force. It's not being compressed. As soon as I say, nope, you can't go any higher like this, now this thing's under pressure. But before that, it was under no pressure because it's just going in one direction. So it's going to move if you don't have those 2 forces balanced. So again, it's kind of like this has weight, right? It wants to go down. Now the weight's balanced. The table is pushing up by the exact same amount the bowl is pushing down, therefore it's static. And so it actually needs both of those. It's a great question. Does this diagram help? That's not meant to be 3D. That's meant to be a side view of it. How do I get from 600 to those two forces? I got that 30 degrees, but where does it go? Yeah, in the picture, it's kind of like right there. Does that make sense? But this is 90, so that means this would be 60, and then this is also 90, so this would be 30, so it ends up kind of going both places. So here's an interesting question. Do I draw the right triangle like this or like this? You see what I'm saying? It's like I need to make a right triangle out of this, but which one do I do? Are they both okay? So 600 really means that's how long this line is right here, right? What's the problem with doing this? That's actually not true. Actually, I said that backwards. What's the problem with doing this?
Oh, you're assuming the normal force is bigger than the 600?
Since this is the hypotenuse, the normal would be bigger than 600. It can't be bigger. 600 is the biggest force there is. It's the large force. So if you make it at some other angle, it's going to get smaller. So I can't draw the triangle that way. 600's got to be the hypotenuse because it's the biggest side. So it is actually this way. Oh, so I could do the cosine of 30 times 600, and that would give me n. Does that make sense? So cosine of 30 would be adjacent over 600. This happened last term too, but it's like that takes a lot of geometric. I don't know about you, but I stare at this and I get a little like, I can't. You got to stare at it a while. You got to turn stuff around, turn it around in your head, draw a bunch of lines, erase them, wad that paper up, throw it away. That's part of it. You should not just look at this and go, oh, I know what to do. And also you should not look for any kind of a memorized thing like, oh, if it's this way, then it's always, cosine. It's like, yeah, what if the cut was going the other direction, like this? So it's like, for me, I just got to draw pictures. In the end, I'll get there. Maybe my method was dumb or a waste of time or something, but it's like, you just got to kind of play around and figure it out. So I think what I did over here is a pretty good illustration of that. So if I take 600 times the cosine of 30, I get 519.6. I haven't paid any attention to units, but 600 was newtons, and so this would be newtons as well. And of course, that looks weird. Normal, newtons, all in the same exact sentence. That's terribly frustrating. So with that, armed with that, I can actually find which one is this? Is this sigma or is this tau? This is sigma because it's the normal one. So I take the force that's perpendicular, which again is not 600, divided by that area that I determined. And since this is newtons and this area is square meters, then I'm going to get an answer that's in pascals. And when I do so, I get 90,000 pascals. What's going to be in the back of the book though? 90 kilopascals. To which I would just say, oh yeah, good, I got it right. What about shear force? Well, do you notice that shear is actually kind of right here? In other words, if you connect these head to tail, like this was our normal force and this would be our shear force. Notice the way I drew that arrowhead, it's going the other direction than what I drew down below. But it's like already in that picture. I don't have to start over again. So it's going to be sine. It's going to be 600 times the sine. So this also could be thought of as V, even though I kind of drew it backwards. But remember, Nothing ever said I should draw it this direction in the first place. It could have just as easily been drawn the other direction. Remember, the concept is, are these two things going to slide past each other? Well, does it slide that way or that way? I don't think it actually matters, right? It's like, are they glued well enough that they can't do that? Could it even slide sideways? Mhm. The key is, it's just, parallel to that plane. It almost doesn't matter which way that points as long as it's parallel.
So Pythagorean theorem by
Nice.
force 519.6.
That's exactly right. I could switch to Pythagorean theorem now that I have 519.6, couldn't I? But it turns out that V ends up, I'll go ahead and write out the trig version of it, but if you said the sine of 30, that would be equal to V over 600, and the sine of 30 is actually a half, so V ends up 300. So tau then would be equal to a force as well, just a different force, a force in a different direction. So shear and normal are just forces. It's just a question of direction, ripping apart or sliding along, divided by the same exact area, newtons per square meter, and I get 51,962 pascals. What is that going to say in the back of the book? What are you going to see? Now think really carefully. There's a rounding problem this time. What's that going to say in the back of the book? I actually wrote this down wrong. Looked in the back. I wrote down 3 places over. I wrote down 51.9 kilopascals. But then I looked in the back and it was wrong. Why was it wrong? That's 6. Makes that 9.
Oh, and then
So it's 52.0 back. It's like, you're wrong, but it's just kind of like get around, I guess. Again, for my purposes, I don't care.
Just write 52, would it be wrong, or do we have to put 0.0?
Good question. It is good practice to say 52.0 because you are telling people it's not rounded to the nearest number. You're telling them how you rounded it. So it's actually good practice to call it 52.0. And notice it's interesting that they're so different. Those two numbers are so different. One of them is sort of the slide number, and the other is the pull apart number, and they're very different. Can you appreciate with respect to gluing something together? That's kind of interesting to wonder, like, how does glue do in that direction versus this direction? Again, that'd be kind of fun to have a materials test and, be able to glue a couple blocks and try to, actually put force on them and see what it took to make them go like this, and see what it took to actually pull them apart. If the glue is good enough, the material could rip apart before the glue. I built an epoxy table at my house and glued basically took 2 slabs of a tree in a row, two 2-foot slabs. So I have an 8-foot by 2-foot slab of a tree, and it's all weird like the side of the tree would be. And I laid them against each other and poured epoxy between them, and then took it apart, sanded it, so forth. Supposedly epoxy is stronger than the wood. If I tried to pull them apart, it would not break at the glue joint. It would break, the wood would rip in half, rip apart first. And you can appreciate with grains of wood, does it make sense? Grains of wood, if the wood is going this direction, that's the direction of the grain. Does it make sense it wants to rip this way quite a bit easier because of different grain patterns, different rings around it and so forth, whereas it doesn't want to rip like this at all. So you got to think about that. Like there's a direction that you need to cut wood to get it to do its job. Yes, exactly. Like a phone book. Let's see, what do we have time for? We have time for one more. Let's do this guy. This isn't new. We just did this. It's just this is a little bit bigger. And so maybe we'll just go a little ways into this. But this is a great question because it involves what you knew from statics. And you can see that in this class, if you don't have statics, you can't take this class. Sometimes it's kind of like, oh, well, you don't really need that prerequisite. But again, this is so practical because you can see this as a part of a truss. And so I got to know how to translate all of these forces through all of the bars. But then I've got to actually convert them to PSI measurements. So notice they did one nice thing for us. They didn't tell us what size those bars were. they gave us literally the area of the bar. So I already know the area. I don't have to calculate it myself. And notice they said the bars, like they didn't even have to, for that reason, tell us whether they were circular or square, because they just told us the area. So, hey, great, thanks. All I need to know is all the forces. But then they also asked me, are these tensile or compressive? So I need to know how many PSI. Well, is that right? PSI, yeah, because it's square inches, so it'll be PSI. But then I have to say it's under tension or compression. Because remember, we're kind of building this thing. There's nothing saying what size bar that is yet. What this is really going to tell us is if we get something like 18 PSI, that's a really small number, but 18 PSI force on this bar and its compression, then we got to go look in a table to see what kind of a bar would do that. Now, the only thing that's a little weird about that is if I change the bar, then that's not 1.25 anymore, right? But again, we're close to actually being able to really design stuff now. Like literally somebody says, I want you to make this thing for me. And you're like, I can do that. I can make all the calculations. How much weight is it gonna have to carry? And then you work the weight all the way through it. And then you go look up in a table based on PSI calculations. And it's like, you know exactly what size material to use and you know how strong the weld at that joint needs to be right there. If that's a pin going through it, holding all three of them together, you could figure out how much force there is that's going to want to shear that pin off and so forth. That's kind of cool. So maybe we won't do all of this just because this is similar to the other one. But notice they did something kind of weird here. Again, they're loading it weird. And you are better at this than the book is. They're just giving a couple of weird arrows aiming at it from nowhere. Again, like books often do. But they say P and half of P, and since P is given to us again as 6,000 pounds, and this would be 6,000 pounds, whereas this is half of that, 3,000 pounds. And I think they wanted AB, BD, CE. Let's just do part of this. AB.
BC 6,000.
I'm sorry?
BC.
BD, CE, BD,
B and C would equal P.
CD. No, CE. Looks like they wanted all the vertical ones. Is that right? CE. Yeah,
Okay.
so actually they just wanted us to calculate the vertical ones, so we didn't have to do them all, which is kind of nice. So, you know, one of my first thoughts is like, is the method of sections allow me to get over someplace without having to do everything? And I'm not really sure, but again, just like last time, notice AB appears to have no force on it at all because 3,000 is pushing to the left. But of course, to get this thing to stay static, I'm going to have to push back on that. And this bar is going to have to do that work. And as a result, it's also going to push up, just like the last problem, isn't it? So we'll at least start this, but this will allow me to get you out of here on time for a change. So if I call this force of AC, I could say awesome. At A, I've got 3,000 going right. Therefore, I need to be doing the sum of the forces in X. So I've got 3,000 right. And because of the arrows I drew, I know AC is going left. And notice again, they were nice because it's a 3, 4, 5 triangle. So 3/5 of AC, force of AC, 3/5 of it is actually going up. I'm sorry, left. And that's all, and that joint's got to stay stable. So I think you get 5,000 for that, just looking at it, force of AC. So does that make it tension or compression? Arrows out is the bar going, pushing out, which is responding to it being compressed. So it's under compression. And of course, right now I could calculate bar AC. However, they didn't ask me for that one. But if I took that number and divided by the area that they gave us, 1.25, I'd have the PSI strength. But let's at least proceed over to bar AB before we quit. Of course, that would mean I'd have to switch to the sum of the forces in the Y direction. And since AC is pushing up, then this has no choice but to pull down, which it has to do on both sides. So I've got force of AC is positive, but 4/5 of it are actually going up. And of course, I'm going to replace that with 5,000 pounds. And then you have AB actually just pulling down, and it is down, so I don't even have to modify it, right? So 4/5 of 5,000 would be 4,000, so I know force of AB would be 4,000. And because it's arrows in, that would be in tension. So then I could proceed and say that the stress in that bar, and again, I'm going to have more than one stress here, so I can't just say stress. I'm going to have to say stress of AB would be its weight in pounds divided by its area in square inches, which is 3,200 PSI. And I already said tension earlier, but in the back of the book, that's probably what I would see. And again, in the back of the book, I might see 3.2 kips there, right? Because that's 4 decimal places, and that's too many. So I might see 3.20 kips in the back of the book in tension. What's cool about BD before we quit? It's exactly the same. You see that? Because although it's connected to bar BC here, BC can only affect things horizontally. So BC effectively has to do all of the 6,000 pounds by itself. And bar A, B, and BD will have to be equal because they're the only ones that are vertical. So I just found the answer to BD. I'm done. BD is the same exact answer. But I am going to have to work my way over to get CE, right? So you don't take your time with questions like this. Like you want to be really good at everything we're talking about here.
So you do have a fun question.
I think you do. Like we could have attempted the method of sections perhaps, but there's not very many of them. But notice it does look like a little bit of work because I'm going to have to get over to joint C. And I now know this one is 6,000. And I know this one was 5,000. Is that enough to get CE right now? The answer, unfortunately, is no. CE is vertical, so I definitely have to do the sum of the forces in Y, but unfortunately, this one is still not calculated. So I can't go to C and do the sum of the forces in Y right now because I don't know what that is. So how am I going to do this? You're going to have to go down here to D first, since this BD is going to tell us what's happening with this bar, and then I could go to C. So actually, I think I have to do everything here. I don't think there was any way out of that. That's a good point. Could you go to C and do the sum of the forces in X first, which would allow you to get this member here? Yes, you could do that, and then switch to the sum of the forces in Y. Good observation. Remember, if this was for a living, you might want to kind of check that both directions and make sure you got the same answer. Incidentally, I got my engineering friend that was my student in high school and went on to be an engineer. He's got a bridge. He's making at somebody's house. It's super common to have like a creek on a property. And so he's doing a replacement bridge for somebody. And he asked me about 2 weeks ago if I wanted to get in on some of his jobs with him, which I'm like, yeah. Number one, I make like $80 an hour doing it, but more importantly to me, it's like cool. I get to design a bridge. I mean, he's actually doing all the stamping, the important stuff. I'm just going to draw pictures of it and so forth. But of course, I'm going to take that as an opportunity to see, does the calculations of that look just like this? And the answer to that I already know is going to be yes. It's like, oh, wow, that's weird. He's making all these calculations, but actually understand all this stuff. It's like that's how you go from being me at $80 an hour, which probably sounds pretty good right now, right? But guess what his is? Guess what his charge is? 140. So the work I have him do for me, for other people, like I just sent a bill off to a person, and my part was 800, and his part was like 1,400. And I'm sure I spent way longer on it than he did.
All he did was
So, but he has to turn in these calculations. Like that's a part of what he turns in. It isn't just a stamp. It's this, like all that writing we've been doing, that's part of what he has to turn in because it kind of goes on record. So that if it actually does break, then it's like, well, he stamped it, nobody understands it but him, so it's like nobody actually checks those calculations. But if something goes wrong, no, it's that, like, it's literally handwritten calculations. There's not a way around this. I mean, like that weird design right there, you could be the first person that ever made that. And so, no, they actually are hand calculations. Very exactly like what we're doing here, so. If it wasn't so late, I'd pull them up and show them to you. But I don't know, I'll let you guys in on that whenever that time comes, but. Rad. All right, you're out of here on time. Be grateful.
Thanks, Doug. For the Oregon PE exam, is there dynamics on that test, you know?
I don't. So with respect to class, we're through 1.5 and then 1.6 and 1.7 are, which is still chapter 1, but we're doing that next Tuesday. So you really should come back with 1.2's questions and 1.5's questions done and for me on Tuesday. Again, there's a little latitude there.
And we got our test on Thursday. Is that 1, 5, and 6 on the test?
All chapter 1 and then 2.2, which is strain. So we got a little bit more to do with this concept on Tuesday, and we're going to do strain on Thursday. And that's going to be outside of class, probably Monday would be my guess. But we'll talk about that. So we're excited. Incidentally, did that system work? Did you like that because it gave you some latitude, or was it like, it sucks because then I couldn't ask any questions? Is there's something we can do to improve that? I'm just thinking I want to preserve class time. Is this
For the test?
class time for me to teach you stuff?
Yeah, it's
Class should not be free credits, so. Do you have any suggestions?